Okay, so good afternoon, Joshua. So welcome to another, I think hopefully, no, last session na natin ito for the analytical chemistry. Let's see. So we're left with a few topics. Like what I mentioned, we'll start with buffer first. Ayan. So last meeting, we discussed about buffers. So when you say buffers, no, ano ang property ng buffers mo? Yung physical properties niya. Ah, anong
Mag-resist
pinaka-physical properties?
mag-resist po
It,
siya ng pH.
very
Ah,
good. It resists pH changes. Hindi ng pH,
opo.
no? May pH kasi siya. Pero once you add strong base or strong acid, the pH will not change easily, no? So instead, it will try to resist the drastic pH changes. Unlike dun sa water, di ba? Di ba sa water, kapag naglagay ka ng strong acid or strong base, uh, automatic, it's either sobrang bababa or tataas yung pH agad, no? So, pero sa buffers, hindi. So, once you um, put strong acid or strong base, it will try to maintain its pH. Buffers are made up of what? Anong components ng buffers mo?
So, ano po, yung acid or base, and it's called
Okay, good anong acid ito? Anong type ng acid? Strong or weak?
weak.
Dapat weak ha. It's either weak acid and its conjugate base or weak base and its conjugate acid. That is the components of buffer solutions. So it means, let's say, Joshua, can we make a buffer out of HCl and sodium chloride? Hydrochloric acid and sodium chloride.
Po.
Again?
Di po.
No, the answer is no. Because HCl is a strong acid. So you will not attain equilibrium there. Kailangan mo ng equilibrium so that you can have a balance, no? Kaya nga siya nagiging buffer kasi nagre-reach siya ng equilibrium eh. Because you can have a balance of your weak acid and its conjugate base or weak base and its conjugate acid. So we can easily calculate the pH of buffer solutions using the Henderson-Hasselbalch equation. Saan natin to pwede ma-derive? Naalala mo to? Can be derived from where?
Yung,
Saan natin na-derive yan? O tignan mo yung mga values.
uh,
May Ka, may H, may A minus, HA.
sa KA mismo po.
Very good. Sa Ka expression ni weak acid, no? So this one can be derived from Ka expression of your weak acid component. So we can also do this for your basic buffer, no? So this is for acidic buffer kasi usually we associate, anyway, regardless naman kung anong type ng buffer, kung acidic or basic buffer, Josh, no? You can always calculate the pH. Pero kapag basic buffer kasi, usually you'll have weak bases, no? So it's easier for us to calculate the pOH, no? So from pOH, you just convert that to pH, no, by having the subtraction from 14. So ngayon, the strength of your buffer refers to your buffer capacity, no? So buffer capacity, basically, strength lang yan ng buffer. So if you will recall, based sa formula, dito lang din yan, no, Josh? Based sa formula, kailan magiging strong ang buffer mo? Naalala mo?
Pag,
Kailan
um,
strong ang buffer? Higher or lower concentration of your components, weak acids and conjugate base? Higher or lower?
higher, siguro
Correct, tama, tama yun. Higher concentration of your
2%.
buffer components, it means they will have a stronger buffering capacity or buffer strength, no? Next, tignan mo yung ratio nito. Ayan. Anong gusto mo sa ratio na yan? Conjugate base and weak acid. Dapat, ang ratio mo ay equal to what?
Equal to yung ano po, yes. Yung ratio na equal to something po eh. special 1 times 10 to the negative 7 ba or something?
Hindi siya, special number siya. Kasi kapag yun yung ginawa mo, logarithm nun, anong mangyayari sa equation? Ano ba ang target mo sa pH mo? Yun na lang muna tayo. What is your target? Buffer pH saka pKa ng weak acid or pKb of your weak base. This
0
should be
po?
what? No, hindi zero yan. pH is equal to pKa plus logarithm A minus over HA.
PKA po. PH equal to
Correct. Yun yung target mo. Ang target mo
so
ay,
make dog 0 po.
good. Yung target mo, yung
1 up.
pH is, yeah. Yung pH mo dapat ay almost close to your pKa. Di ba recall, paano ka nga pipili ng acid? May target pH ka, pipiliin mo yung pKa na ano yung range? Plus, minus what? Plus, minus, anong pipiliin mo na buffer? Na weak acid ng buffer mo. Dapat yung sa target pH mo, let's say ang target pH mo ay 4.5. Ano dapat ang pKa ng weak acid mo? Plus minus what ng pH?
Plus minus, special number din po yan. Plus minus 7 ba po or something?
No, hindi.
Ah,
Ang laki noon. Pag range mo ay 7, mahaba yun. Plus minus, o sige, andito
opo.
na tayo. Ayan.
Ah,
Hmm.
yung ano na po may range po yung mga buffer kasi. So,
Yeah, correct. May range nga sila. Ano yon? Ano yung
yung
range nila?
sinasabi ka, yung within na po yung of their PKA, di,
Oh.
ganito, tapos yung acetic acid, may ganun siya.
Correct.
Ah,
Kasi optimum pH nila or optimum pH ng buffer mo kung equal siya
1
sa
po?
pKa.
Minus 1?
Plus
Plus
minus
minus
1. Okay, so pakitandaan to dyan siya. Let's say, ang pKa ng buffer ng acetic acid is 4.76 if I'm not mistaken. So yung buffer na makaya niya magawa ay hanggang saan ulit na range? Uric acid, let's say acetic acid. So acetate buffer ang gusto mong gawin. So your acetate buffer will act as a buffer in what ranges?
3.76
From
hanggang 3.76.
Okay, hanggang dyan lang siya magiging buffer. Okay? That is your buffering region. Kumbaga, no? This is buffering region of your acetate buffer. So if your target pH is within this buffering region, it's empirical that we can use acetate buffer. But if you want to have your buffer, let's say ang target pH mo ay 7, you cannot use acetate buffer because beyond 5.76, your acetate buffer is not a buffer anymore, no? So normal na lang siya na solution na may acetate, no? Tapos pag naglagay ka ng ano diyan, ng strong acid or strong base, mabilis magbabago yung pH. So ang clue dito, dapat alam mo na bawat buffer will vary depending on your target pH. No? Depending on your target pH. Ngayon, ang clue mo dyan, tinignan nga natin yung table last time, di ba? Yung Ka table. Doon kasi may kita mo rin yung pKa nila. Para makakuha tayo ng, let's say, if we want to prepare a buffer solution na target pH ay 7, we need to find a weak acid na ang pKa niya ay near 7. Okay, so that we can create your buffer. So, if you want your pH and pKa almost equal, Josh, babalik ako sa tanong dito. Anong gusto mo dun sa ratio ni conjugate base and nucleic acid? Yun pala ang target mo, Josh. Almost equal si pH and pKa. So,
Yun nga po.
anong
So make a make the log A at A over HA equal to 1.
1? Kasi ang log 1 ay equals to what? Log 1 is equal to what?
Log 1 is equal to 0.
Kaya ang mangyayari, if log 1 is if your A minus and HA are almost equal, no? So almost same sila ng concentration. This one will be log 1, no? So 0 na to. So ang mangyayari, pH is equal to pKa. Kaya maganda yung mas magiging strong, no? Yung buffer na mabubuo mo. So last meeting, dito tayo nagtapos, no? How we will prepare um, the buffers, no, using the Henderson-Hasselbalch equation. So like what I mentioned, number one, know first your target pH. Pag alam mo na yung target pH mo, Josh, hahanap ka ngayon ng weak acid na ang pKa niya ay near sa target pH mo. Pakitandaan yan, Josh, ha? Again, so you need to find a weak acid wherein its pKa is quite near to your target pH. And then from there, so once you have your weak acid, kung nakita mo, target pH mo ay 7. So nakita mo, ay si phosphate buffer ay okay dito. Ngayon, hahanapin mo na yung conjugate base niya. Usually salt, no? So, ngayon, let's say, ang target pH natin 4.5. Balik tayo kay acetate, no? So of course, pwede natin gamitin yung acetic acid, no, as your weak acid. The conjugate base of your acetic acid is acetate. So anong salt ang pwede mong gamitin, Josh?
Ah, yung
Anong salt?
ano,
Acetic acid ang weak acid mo. Anong salt ang pwede mong gamitin?
baka siguro sodium acetate po will work.
Yeah, sodium acetate. So basta may acetate, yun yung mahalaga. Pwede yung magnesium acetate, potassium acetate, anything na may acetate, Josh, will work as its conjugate weak base. No? So, from there, prepare concentrations of each weak acid tsaka yung conjugate base mo. No? And then, you calculate the ratio so that you can determine the buffer concentration. So, once you've done that, mix together the weak acid and its conjugate weak base, and then hopefully, no, uh, pag nag-mix mo na sila, you will form a buffer solution already. Ang problem mo dyan, Josh, eto pala yung hindi ko ito na-highlight nung last time eh. Ang problem mo dyan, Josh, let's say, pag pinag-mix mo si acetic acid and si acetate, no? So, you mix acetic acid and your acetate in your solution. Let's say, ang target pH mo ay 4.5. No? That's your target pH. Pero pag minix mo na sila, in reality, Josh, hindi mo kagad mabubuo yan. Hindi mo kagad makukuha yung 4.5. Let's say ang nakuha mo ay 4.6. Ito yung pH meter reading mo. Anong gagawin mo? Yan. Minix mo na sila. Tapos nagbasa ka sa using pH meter. Hoy, hindi 4.5 yung nabuo ko. 4.5 ang target mo. So, 4.6 yung nakuha mo. Paano mo yan i-adjust? Kasi nakalagay dyan sa last step, adjust
Type,
pH.
type 3.
Again,
Type 3.
titrate? Hindi naman titrate, pero it's like a titration.
Dilute.
Hindi ka pwede mag-dilute dyan. Kasi pag dinidilute mo siya, ganun pa rin yan. Yung pH mo ay magiging 4.6 pa rin.
Kasi same number pa ayaw na po.
Mhm.
Natanggal?
Hindi. Paano mapababa or mapataas ang pH?
Magkano po ng something ion po para mag-ano
Hindi
siya?
naman ayon. Anong acids and bases to eh? Sa anong i-add mo?
Opposite na po, some base or acid.
Very good. Anong type ng acid or base?
Conjugate
Strong
na po.
or weak? Strong or
Mm,
weak?
weak.
Hindi. Ang ina-add mo dyan ay strong.
Pero super
Kasi,
diluted lang.
oo, depende naman niya. Kasi tandaan mo dyan siya, hindi naman kaagad-agad magbabago yung pH mo, no? So, when you say adjusting pH, pakitandaan ito dyan siya, when you say adjust pH, add either, depending on the situation, no? Add either usually 0.1 molar HCl or 0.1 molar NaOH. Dropwise ito, ha? Add dropwise either 0.1 molar HCl or 0.1 molar NaOH. In our case, ano ang gusto mong mangyari, Josh? Sa reading ng pH meter mo, 4.6. So, anong i-add mo sa acetate buffer mo? Eh, ang target mo ay 4.5.
Strong acid po.
Strong acid like 0.1 molar HCl. So mag-a-add ka ng 0.1 molar HCl until dropwise yan ha. Tinitignan mo yan parang habang nakababa din yung solution mo no, tsaka yung electrode mo ng pH meter tapos may steering, continuous steering yan, naka-magnetic steerer. Mag-a-add ka dropwise ng 0.1 molar HCl until you reach 4.5. Pag na-reach mo na yung 4.5, hinto ka na sa pag-add, no? Tapos, yun na yun. Makukuha mo na ngayon yung target buffer mo, no? With the correct pH. Okay? So, let's move. Ngayon, eto, dito na tayo, no? So, let's say we'll have an example. What is the pH of a buffer that is 0.12 molar lactic acid? So, lactic acid is this one, no? Tapos, ang Ka ni lactic acid, hindi to HCl na. Dapat ano, i-sure natin to. Hanapin mo nga yung Ka ni lactic acid. Ka, lactic acid. Kasi nakalagay dito sa ano natin ay ano, HCl eh. No? So, baka mali lang siya.
Oh, PKE
Ah,
pero yung PKE.
madali naman i-calculate. Kunin ko lang din yung calcul ko, Josh.
1.4 times 10 to the negative 4 po. Tama na po.
Tama siya? Okay. So, tama naman pala. So, ibig sabihin nito, hindi yan HCl, no? Lactic acid yan. Yan. So the Ka for lactic acid is 1.4 times 10 to the negative 4. So this is correct ha. This is not hydrocyanic acid. This is lactic acid. And then, minix mo daw yung lactic acid mo na 0.12 molar ang concentration with 0.10 molar sodium lactate. So this is the formula. So this will be the equation na mangyayari, no? Or reaction rather, na mangyayari. So your lactate will dissociate into hydronium ion, tsaka your lactic acid will dissociate in water into hydronium ion and into lactate. So with that, ito madali tong problem na to. You just substitute everything dun sa Henderson-Hasselbalch equation. So, ang may mali dito, no? Ang mali dito, pH is equal to dapat negative log of 1.4 times 10 to the negative 4 plus logarithm ng base over acid. So ngayon, Joshua, pag gumagamit ng Henderson-Hasselbalch equation, it's very important that you know who is the acid and who is the base. This one, it's easy. It's already mentioned, no? Lactic acid is, of course, yung nasa ilalim, 0.12 molar. And then, si lactate, yung sodium lactate, no? That will be 0.10. And then, once you perform this calculation, your pH is equal to 3.77. No? So, pasok ba to dun sa buffering region ni lactate? So, let's say if you have a lactate buffer, Josh, anong pKa ni lactic acid? pKa ay 3.86 sa akin. Sa na-search ko.
Pasok
So,
po siya.
pasok ba? Okay, good, no? Kasi buffer, ang lactate mo from 2.86 up to 4.86. And we can see 3.77 is really near dun sa pKa ni lactate buffer. No? So, 3.86. This is really near. So, it means, Josh, yung nabuo natin is a strong buffer, no? A strong lactate buffer. No? Kaso lang, hindi natin pwede masabi na strong lactate buffer siya without another lactate buffer no, in comparison. So, para kung magkakaroon ka ng comparison, tignan mo to, Josh, ha? Let's say, ito naman yung mangyayari. Ang lactic acid mo ay 0.05 molar. Tapos ang sodium lactate mo, sodium lactate. Yan. Sodium lactate mo, yan. Wait. Erase ko na lang. Your lactic acid is 0.05 molar. Tapos, yung sodium lactate mo ay, let's say, 0.04 molar. Can you calculate the pH, Josh? Calculate nga. Yan, ganun pa rin yan, base over acid. So, 0.04 over 0.05. What is the pH for this?
Opo.
You'll still use the same Ka, which is 1.4 times 10 to the negative 4. Kasi ang weak acid mo naman ay si lactic acid pa rin, no? Hindi naman siya magbabago.
3.94.
3 point?
94 po.
Okay, tingnan mo. Ayan, this is a good comparison. Sinong stronger buffer? Yung first one na 3.86 o si 3.94? Tingin
Mm,
mo. Tsaka bigyan
3.94.
natin ng reason.
3.94 po.
Bakit si 3.94 ang stronger buffer?
Malapit po sa PPA.
Mas malapit sa pKa. Ano ba yung pKa ni ah ni lactic acid? 3 point?
Mas malapit po yung 3.77 sa 3.85.
3.85. Okay. So, 3.86. Ano pa? Depende mo yung answer mo. Bakit siya?
Malapit po yung pH sa PK.
Mas malapit. Yun nga yun, yung sinabi mo. So, I mean,
Mm,
sino na yung sagot mo talaga? Yung
3.77.
3.77. Sure na? Final answer?
Mm,
Babalikan mo yung mga pinunto natin kanina, yung mga points natin on how we can tell if a buffer is strong or not. So, correct, no? Number one rule is check the pKa and your target pH. We can see here, medyo magkalapit kasi sila, no? 3.77, then 3.85, then 3.85, 3.94. So, medyo malapit naman. So, ibig sabihin, parang pwede nating sabihin, hala, parang equal strength sila, no? Based dun sa based dun sa pH ng buffer mo. Ang susunod mo ay yung concentration nila. Tignan mo, sino yung mas marami, Josh, na lactic acid and sodium lactate ratio kumpara dun sa isa.
kung dinadaganin naman po yung isa.
Hindi. Mas madami, mas maganda. Pero dapat ano ha, almost pantay. Almost pantay. Kaya tricky yan. Kaya tricky yan, no? Kaya kailangan mo ring um, aralin. Ito okay to, 0.12 to 0.10. Okay yan, magkalapit yan, no? Tapos ito 0.05, 0.04. Okay lang din yan. Ngayon, ang stronger buffer dyan, Joshua, the answer, of course, is tama ka naman yung 3.77. Stronger buffer ito. So aside from your pH is quite near to your pKa, aside from that, the concentrations of your weak acid component and then its conjugate base is higher in value or higher in concentration compared to your 3.94 buffer. The 0.05 at 0.04 molar lang yung concentrations ng components mo. Okay? So, ayan. Ayan. Meron pa akong isa-solve dito. Ngayon, ito, preparation ng buffer. Kasi in laboratory dyan siya, in laboratories, preparing buffer is a skill. No? So, skill yan and at the same time, may theory ka dapat behind that. No? Kaya dapat kabisado mo yung Henderson-Hasselbalch equation. Sa aming mga chemist, no, ano yan, matik yan na dapat alam namin yung Henderson-Hasselbalch equation. Because usually we prepare buffers uh, in laboratories. So kapag ganyan, you follow the formula, no? pH is equal to pKa plus log base over conjugate base over its weak acid. So this is the question. How many moles of sodium bicarbonate? So this is the ano ito? Sodium bicarbonate. Rinig mo pa lang, salt kagad siya. Ano na yung ina-expect mo dito? Siya na yung magiging sodium
Element.
bicarbonate. Anong component siya ng buffer mo?
Yung base po.
Correct. So, siya na kagad yung conjugate base mo, no? Yan. Kasi salt siya eh. Should be added to 1 liter, so may 1 litro ka daw, ng buffer na 0.1 molar carbonic acid. No? So, you have you have 1 liter of 0.1 molar carbonic acid. Actually, carbonic acid alone is a weak buffer, no? Yung mismong carbonic acid, weak buffer na yan. However, mas mapapastrong mo siya kung dadagdagan mo siya ng conjugate base niya, which is sodium bicarbonate. No? So, ang Ka ni carbonic acid ay 4.2 times 10 to the negative 7. However, may tanong ako, Josh. Ilang Ka dapat si carbonic acid?
Mga ano po niya, no? Mga
Ilang Ka?
4.2
Tignan mo
times
lang.
10 to the 7.
Hindi, hindi. Ilan ang Ka niya? Ilan ang dissociation niya?
4.2 nga po times 10 to the negative 7.
Oo, ilan ang dissociation niya? Hindi, I mean, I'm not asking for the value of the Ka. I'm asking how many dissociation will your carbonic acid
Yung
undergo?
ah ah dalawa. Mahigit
Dalawa,
pa.
correct. Tama, tama. Dalawa. So, magiging plus H2O. So, magiging HCO3 minus plus H3O plus. Correct? Tapos, itong bicarbonate mo, pwede pa ulit mag-react sa water to form this time carbonate ion 2 minus plus H3O plus, no? So that is your carbonic acid system. But usually ang nangyayari kasi kay carbonic acid, nagiging ano yan, bicarbonate yan, no? Tsaka water. Bicarbonate tapos ah, carbon dioxide and water. Basta you will form your bicarbonate. So, yung 4.2 times 10 to the negative 7 is associated to what? Kanino kaya yan? Tingin mo. Kanino yan associated? Sa first or sa
Oh,
uh, second?
first.
Hmm? First or
First po siya.
second?
First.
Okay, correct. So, sa first yan associated ha. Dito yan. Ito medyo mataas na yung value nito. Try mo nga hanapin dun sa table natin kung ano yung value nito. Para lang marunong ka maghanap. Bicarbonate to carbonate. So, hanapin ko din. Try ko hanapin. Ah, dalawa kasi ang PA niyan. KA and pKa values. Okay. Ano nga yan? Carbonic acid. Hmm. Ah, isa lang siya dito. 4.3 times 10 to the negative 7. Tapos ang binigay niya, yeah, bicarbonate tsaka H2CO3,
Carbonate
carbonic
po is
acid.
4.7 times 10 to the negative 11.
4 point?
7 times 10 to the negative 11.
O, di ba? So, ang tagal bago matanggal pa to si bicarbonate, no? Napakaliit. So, parang ano, the formation of carbonate ion is less preferred, no? Once you form the bicarbonate, medyo okay na tayo doon. Tapos, si carbonate mo, medyo mahihirapan ka nang mabuo yan. Kasi times 10 to the negative 11 na yung Ka niya, no? So, ayaw na ni bicarbonate mag-dissociate. So, pwede na siya dyan. Kaya usually, ang Ka1, technically ha, Ka1 po ito ni carbonic acid. And this is your Ka2 for your carbonic acid. So, that is a Ka. To prepare a buffer with a pH 7. So, let's analyze first if this is logical. Can we prepare a buffer, a carbonate buffer na ang pH ay 7? Josh,
Opo. If we
bakit?
dilute that,
Ano deleted? Hindi. Ano titignan mo para malaman mo logical yung na ang target pH mo ay 7. Tapos,
yung
carbonate buffer ang
pH,
bubuin. Yung pKa, ano ang pKa value mo?
hindi ko po alam. Mga, ano kaya?
O, i-calculate mo.
Negative 12.
4.3 ba yan? Times 10 to the negative 7.
Mga 6.37.
Correct, no? So 6.37. So if that is the case, so 6.37, we can clearly see, no? As target pH mo naman ay 7 eh. So this is from 5.37 to 7.37. So we can still use carbonic acid and sodium bicarbonate to form a buffer na ang target pH ay 7. So with that, ngayon, ang tanong kasi dito ay, ah, paano ka magpre-prepare nun, no? Meron kang 1 litro ng 0.1 molar bicarbonate, may Ka ka na, ang target pH mo ay 7. So, ang nawawala mo dito, mass nito. Ayan, yung mass nito, no? Yan ang hahanapin mo ngayon. So, we just substitute 7 here. Tapos negative logarithm ng Ka plus logarithm, if you will notice, ayun, bakante ngayon to, then 0.1. Since ang volume mo naman ay 1 liter, maka-cancel out mo na yan. No? So, maka-cancel mo, same volume sila. So, we can assume here, moles na ito. No? Magiging moles na ito, then moles ang makukuha mo. So, moles ni bicarbonate ang makakalculate natin. Simplifying the equation, so let's say, pag makuha mo na to, let's say 6.37, itatranspose mo lang, or 6.4, no? Itatranspose mo lang, magkakaroon ka ng difference ng pH minus pKa kasi ang mangyayari, ayan, no? Lipat mo siya. pH minus pKa, which is 0.6, no? Equals logarithm nito, kung may iwan nito. And then, to remove the logarithm, i-antilog mo siya, no? So, pag in-antilog mo yan, magte-10 raised to something to lahat, no? So, magiging 10 raised to 0.6 equals 10 raised to logarithm bicarbonate over 0.001. Then, cancel ngayon to. Or 0.1 ito. Bakit naging 0.001? 0.1 yan, no? Yan, 0.1. And then, once you have that one, no? So, since wala na yung logarithm, pwede mo na ngayon i-calculate kung si bicarbonate. So, bicarbonate is equal to 0.1 times 10 raised to 0.6, which is equals to 0.4 moles, no? So, ngayon, paano mo to gagawing mass, yung 0.4 moles?
Ah,
Excuse po. Hanapin mo yung
molar
molar
mass.
mass ni, okay, very good, ni sodium bicarbonate. Anong molar mass sa sodium bicarbonate? Hanapin
Ah,
natin. Ako, hinahanap ko na
okay.
lang. 84.01. So, sodium bicarbonate, lagay ko na muna dito. 84, yeah, 84.01 grams per mole. So ngayon, if that is the case, Josh, alam naman natin na based sa formula, meron kang 1 mole ng bicarbonate. So therefore, we can directly, ano to, no? Gusto ko lang ipakita yung stoichiometry. So may 0.4 moles ka ng bicarbonate. So pakitandaan, may 1 mole ka ng bicarbonate kasi baka masanay ka na i-multiply mo lang kagad. Hindi. Analyze mo yung formula. May 1 mole ka ng bicarbonate sa 1 mole ni sodium bicarbonate. Kasi baka malay mo yung conjugate base mo ay dalawa pala dun um, sa formula. Kaya ang mangyayari diyan, i-divide mo siya sa 2, no? So tapos sa 1 mole ni sodium bicarbonate, meron kang 84.01 gram grams ng sodium bicarbonate. So ayan, kitang-kita kasi dito na from moles ng conjugate base mo, naging moles na siya or naging grams na siya rather ng ating uh, salt, no? Yung salt ng conjugate base mo. So what is the answer? 0.4 times 84.01. Pa-solve, Josh. Kasi 0.4 moles lang ito eh. Tapos siya ka natin i-describe paano siya i-prepare. Sa bagay, ang tanong lang dito, how many moles eh, no? Pero,
33.6.
again,
33.6.
23.6,
33 po, point.
point what?
33.6.
6.
Opo.
Okay. 23.6 grams sodium bicarbonate. So,
33 po.
paano? O, madami-dami, no? Pero 1 litro kasi to. 1 litro
33
yan,
po.
Josh, ha?
33. 33.
33, sorry, 23.3. Madami-dami pa rin siya. But if you will notice, 1 liter kasi ito ng buffer. So, paano mo siya gagawin sa laboratory? Ang unang-una mong gagawin, Diyos, prepare first a 0.01 or 0.1 rather, 0.1 molar carbonic acid. Yan muna ang una mong gagawin, no? So, 1 litro dapat yan. Tapos, anong gagawin mo? Weigh out. Yan. Meron ka na ngayong 23.3 grams nino, sodium bicarbonate. Tapos, tsaka mo siya ihahalo and then stir. Okay? Stir mo siya ngayon. So, after ma-dissolve ni sodium bicarbonate sa 1 litro ng buffer mo, ni 0.1 molar carbonic acid, H2CO3 na wala ang C. Ayan, H2CO3. After yan ma-dissolve, Josh, ni sodium bicarbonate, dyan sa 1 litro ng carbonic acid mo, you will form a buffer na ang pH ay 7. Pero sabi ko nga sa'yo, hindi yan siya, carbonate buffer niyan, hindi marireach lagi. Lagi yan dyan siya, sobrang galing mong mag-prepare ng solution. Kapag ang target pH mo, na-hit mo kagad, no? Isang preparation lang, na-hit mo na kagad. Lagi siyang hindi. Kunwari, very critical kasi yung pH minsan lalo sa studies. Pero minsan naman, ako hindi ko na minsan chinecheck sa pH meter kasi alam ko na yung pH range. Eh, hindi naman siya ganun ka critical sa reaction, kunwari yung pH. Okay na yun, no? Once you, basta, ang mahalaga, you prepare a buffer na based sa hinihingi nung problem or nung experiment. So, kasi kunwari, target pH mo 4.5, tapos nag-prepare ka ng phosphate buffer o kaya carbonate buffer, no? Very impossible yan na pH 4.5 makukuha mo. Anyway, hindi 7 ang makukuha mo dyan. Let's say either 7.05 or 6.98. Ngayon, anong gagawin mo para ma-adjust mo yung buffer pH? Kung nga ulit ang gagawin, Josh, to adjust the buffer pH?
Maglagay nga po ng, ano, maglagay nga po ng opposite.
Correct. Maglalagay ka ng strong acid or strong base. Depende dun sa pH na nabuo. Compare that to your target pH. If it's lower, let's say 6.98 ang nabuo mong pH, ano ang ilalagay mo dun sa buffer? Strong
Okay.
base. Strong base. Usually, 0.1 molar NaOH. Kaya usually sa mga labs, Joshua, may nakareading 0.1 molar. Lagi yan. May nakareading 0.1 molar HCl and 0.1 molar sodium hydroxide. Kasi pwede din siyang gamitin sa pang-adjust ng buffer. So let's say kung 7.05 naman yung naging nabuo mong pH, eh target pH mo ay 7 and very critical yan sa mismong reaction mo, you add a strong acid hanggang ma-reach mo yung 7. Okay? Yan, ganun ang pagsagot, Joshua. Let's say kung ang tanong ay describe the preparation of a carbonate buffer na 1 liter, 0.1 molar carbonic acid na ang target pH ay 7. So, calculate mo muna yung mass si sodium bicarbonate. So, ang tamang sagot ay ganito. Prepare first a liter of 0.1 molar carbonic acid, tuldok. Then add 23.3 grams of sodium bicarbonate into the solution. Stir until all of your sodium bicarbonate will be dissolved. No? Once dissolved, check the pH and adjust the pH by adding either 0.1 molar HCl or 0.1 molar NaOH. Yan ang proper answer kapag preparation of buffer ang tinatanong. So with that, ikaw ngayon yung magsasolve nito. Same problems naman ito, no? Dun sa sinod ko. Sa number 8, take note mo sa number 8, medyo kakaiba yan dahil ammonia yung binigay. Calculate the pH of a solution that is 0.2 molar in ammonia and 0.3 molar in ammonium chloride. No? So the Ka for ammonium ion is 5.7 times 10 to the negative 10. Then sa number 9 naman, Josh, describe how you might prepare approximately 500 ml, so 500 ml lang, na ang target pH mo ay 4.5 buffer solution from 1.0 molar acetic acid and sodium acetate. Pakitandaan nyo siya, 500 ang target mong pH. I mean, ang volume, rather. 500 ml lang, no? Tapos, may 1 molar acetic acid ka na. So you try to screenshot this the problems first. Tapos tsaka natin i-solve dun sa ano mo sa Jamboard. Na-screenshot mo na, Josh? Okay na? I'll stop sharing na ha. We're good? Okay na?
Opo.
Okay. Oh, you can just share. Stop sharing. Then share mo yung Jamboard mo. Tapos solve mo yung 8 and 9 na yan. No? So, yung una dyan is just calculation ng pH ng buffer. No? Yung second problem mo, preparation. So, kailangan narrative yung sagot mo dyan. So, pag ganyan ha, alam mo naman na to eh, kasi naggaganyan tayong mga problems last time, no? Kaya nung sa Gen Chem pa lang natin, ganyan na, may mga ganyan na tayo, yung, lalo na sa preparation ng solutions. So, describe how you might prepare 500 ml of 4.5 buffer solution, pH yun, na from 1 molar acetic acid and sodium acetate. Okay? Sige, go ahead. You can now share your Jamboard. Siya. Dito lang isara ang mga windows. Okay. Share now your Jamboard. Yan. So, good. Oh, anong formula mo ng ano? Mhm. Ako din. What's your Henderson-Hasselbalch equation, Josh? Naku po, ayan. Number 9. So, correct. Dapat nga, how will you prepare yan eh? Sa old book yan. Sa old book ko yan kinukulit. How will you prepare that? Or describe the preparation. Hmm. Madali naman yan, acetic acid lang yan eh. So, dapat alam mo na ako, actually, dahil sa paulit-ulit yung acetic acid na example, kasi isa siya sa pinakamadali, mahanap din na compound no, or na substance sa lab. Makakabisahan mo talaga yung ano niya, Ka. Mhm.
Kinain ko po yung ampalaya, raw. Ay, yung plain.
Ano ba ang ano mo, ulam ngayong gabi? Ampalaya?
Opo. Negative sa 2.2.
Remember ha, may volume ka dyan, Josh. Tsaka 0.55 siya. Naka-logarithm pa yan. Di ba? 0.55 equals logarithm of x over 1.0.
Inano ko na po siya.
Nakaano na yan?
Opo.
Hindi siya proper kasi dapat ah 4.5 minus 4.76. Mhm. Shift at below. Sige. Okay. Yeah, pwede na. Diniretso mo lang kasi. Yan ang concentration mo, 0.55 molar din. Okay, good. Kasi nga, ano mo siya, 500 ml lang naman yung. Paano mo i-prepare? Describe the preparation.
No.
Hindi kasi siya hindi ganyan yung final answer. Mhm.
Measure, ano po, measure 22.640 grams. And
Mm-hmm.
then simply dump it inside, simply dump it into the,
Dump it
dump it,
into the
dump it into the bigger pot. That,
Dump it into the beaker containing what? Okay, containing 1.0 molar HCl. HCl, tuloy, acetic acid.
it's as
Okay.
simple as that.
Okay. So I think we're good with that problem. So let's go back now to our um, discussion. Or just keep your Jamboard kasi baka may solve ka pa. Let's now proceed with hydrolysis. Okay. Okay, I think you can now see my presentation. We're good with this one. Yan. So ang susunod ay salts of strong or weak acids and bases. So let's proceed first with salts ng strong acid or strong bases. So strong acid and strong bases will produce salt with weak conjugate acids and bases. So therefore, virtually, no, virtually or theoretically speaking, let's say ito si HCl. Di ba strong acid naman to, Josh? So we will have a full arrow, no? One-headed arrow lang siya to form H3O plus Cl minus. So this is my question. Cl minus is what again, Josh? By Bronsted-Lowry definition. Sino si Cl minus? Okay, good. Conjugate base ni HCl. So this is my question. Can Cl minus react with hydronium ion or let's say water? So let's say pwedeng ganito siya, Joshua. Cl minus plus water. Kasi si water mo ay pwede di bang ano to, acid base? So that you can form HCl. O yung babalik tayo sa HCl plus OH minus. Can we have this? Is this feasible? Okay, correct, no? It will just dissociate immediately. So once you form, correct. Once you form this HCl, it will go back again to Cl minus. So this is not theoretically acceptable. No? So hindi yan. So yung hydrolysis, ibig sabihin, yung mga conjugate bases and conjugate acids of strong acids and strong bases, respectively, they will not form back the strong acid nor strong base, no? So again, strong acids and strong bases, their salts with weak conjugate acids and bases, they will not form back the strong acids and strong bases anymore. So therefore, hindi kayang mag-react. So this is the clue, Josh. Yung mga conjugate acids and conjugate bases coming from your strong acids and strong bases, they cannot react with water or cannot make water to undergo hydrolysis, no? So therefore, their pH is close to neutrality. Close to neutrality yan. So let's say, ayan, if we mix HCl and NaOH, we'll have sodium chloride, which is approximately 7. Yan yung nangyayari sa mga salts ng strong acids and strong base. So let's say, ang strong acid mo ay sodium chloride, no? So pH yan ay near 7. Okay? So, yan ngayon yung situation for strong acids and strong bases. Para madali mo palang maano din Diyos siya, let's say kung ano siya, mag-undergo ng hydrolysis or hindi. Identify mo lang kung weak acid or weak base siya. Kung anong type ng ng electrolyte, strong ba siya or weak. Kasi ang mga strong, automatic yun, usually they will form ions immediately. And usually their pH is, sa mga salts ito their pH are usually near 7. So kunwari, sodium chloride, ito. So ang sodium mo saan galing? Sodium hydroxide. Ang chlorine mo ay galing saan, Josh? Sa HCl, no? So, ngayon, this is a strong base and this is a strong acid. So, therefore, this is a neutral salt. Ang tawag natin dyan ay neutral salt. No? So, dito ba yan sa slide natin? Yan, ito. Salts whose ions are aprotic or aprotic salts. Yan. Pwede rin yan. Neutral salt or aprotic salt. Yan. Aprotic salt. Yeah, this is safe to drink. Oh, you will know, safe to drink naman ng acid. Ngayon, however, ito ngayon yung yung mangyayari. Paano yung mga salts na pwede maging weak acid or weak base, no? Paano yung mga salts na gano'n? Okay. Charger. Paano ang mga salts na gano'n, Josh? So, galing sila sa weak acid or weak base, kumbaga. So, let's say we'll have sodium acetate. Ang sodium acetate saan galing, Josh? Sodium. So, sodium hydroxide, correct? Acetate from acetic acid. So, this is a strong base. This is a weak acid. So, ano ang sodium acetate? Ano ang sodium acetate? Anong type siya ng salt? Medium? Hindi. Tignan mo, sino yung strong part sa kanya? Sino yung strong part sa kanya? Yung base. Basic salt ngayon siya. So, this is a basic salt. Basic salt yan. Okay? So, that's a basic salt. Sodium acetate is a basic salt. So, if you will notice, this is the pattern. If you have weak acid, it will form a strong conjugate base. Or a weak base, it will form a strong conjugate acid. Therefore, if you will have their salts, no? If you will have their salts, hydrolysis will occur. What is hydrolysis again, Josh? Hydrolysis? Hydrolysis. Okay, splitting up of water lang yan. Okay, very good. So, ini-split up nila yung water, no? So, ayan, kunwari, may cation ka. So, usually, these are your conjugate acids, no? Your conjugate acid reacting with water, it can form this salt, then hydronium ion. Then your anion, usually conjugate bases, reacting with water to form this salt, tsaka tong hydroxide ion. So, yun yung nangyayari sa no, sa mga salts mo ngayon. So, ang tanong kasi dito, Josh, paano kung salt lang yung nilalagay mo dun sa tubig, no? Kasi yun yung question. Paano nakukuha yung pH, no? Madali kapag kapag neutral salt or aprotic salt, 7 agad yan, mate. 7 agad siya. So, ngayon, kapag an ion, let's say yung acetate mo, so sodium acetate, release OH causes the pH of the solution to increase. But example, sodium acetate. Sodium acetate contains acetate ion, which causes hydrolysis. So, isusulat mo yung hydrolysis reaction ng salt. So, ito yung hydrolysis, yung conjugate base mo reacting with water, you'll form acetic acid at saka hydroxide ion. So, what do you expect? Pag nag-dissolve ka pala, Diyos, ng sodium acetate, anong pH mo? Greater than 7 or lower than 7? Sodium acetate. Si sodium acetate ay isang basic salt. So ano siya? Very good. Greater than 7 agad. Tingnan mo, ito yung tanong ko eh. Dati tanong ko rin to nung undergrad ako. Tingnan mo, ano yung nabubuo mo once your salt will cause hydrolysis to your water? Anong nabubuo mo? Oh, hindi sodium hydroxide. Tingnan mo to, ito lang oh. Okay, di ba may acetic acid ka? Hindi ba ito rin ay pwedeng bumalik? Tapos H plus naman yung mabubuo niya. 'Di ba? Tapos ika-cancel out niya 'to. 'Di ba? That's my question ha. Tingnan mo, may acetate ka. You have acetate. And then nag-react sa water, hydrolysis. Ngayon, nag-form ka ng acetic acid. NOH minus. 'Di ba yung acetic acid ay nag-dissociate din? Kasi weak acid yan eh. Kaya niya mag-dissociate. into acetate and hydronium ion this time. So ngayon, magiging futile yung reaction kasi i i-neutralize nyo lang si OH minus. Okay. So, good. But acetate is a weak acid. Hindi na ganun kalaki yung contribution ng H+. Meron man, maliit na lang. Kaya it will make, or parang ganito, ang dominating species mo ay si acetate. Kasi siya naman talaga yung nilagay mo sa tubig, no? Let's say you have your water. You just added sodium acetate. You did not add, no? Um, acetic acid. So therefore, acetate ions ang madami doon. Once you have your acetate ions making or forcing your water to undergo hydrolysis, you will now have acetic acid. Very few din naman yan kasi equilibrium din to. Take note, Josh, your acetate itself, the hydrolysis itself, it's an equilibrium reaction also. So you will not produce a lot of acetate, no? Or acetic acid rather. You will not produce a lot of acetic acid. So therefore, sobrang liit nung manggagaling na H plus from the dissociation of your formed acetic acid, no? Vinegar powder. So yeah, you have more OH minus this time. Okay? So, we can differentiate or we can classify based dun sa ano kanina, we can classify your salts. So, etong hydrolysis na topic na to, Josh, salt in water ito. Yan ngayon yung ano mo, Josh, dilemma. Kasi 'di ba tignan mo kung sana na nagigets mo yung pattern natin Kasi sabi ko sa iyo, ginagawa lang natin, ini-scrutinize lang natin yung discussion. We started with water, correct? Then yung water, nilagyan mo ng acid. Either strong acid man yan or weak acid. Yung water, nilagyan mo ng base. Either strong base or weak base. And then after nung kanina, no, yung water, nilagyan mo ng weak acid and its conjugate base or weak base and its conjugate acid to form a buffer. No, we're always dissolving something in water. So this time, may salt ka ngayon na nilagay sa water. What is the pH, no? Parang ano yung magiging property niyan? So, ngayon, it depends on the classification of your salt, no? So, we can classify salts into four. Number one, salts whose ions are aprotic. So, let's say sodium chloride, no? So, when you say aprotic salts, neutral ang nabubuo nila, Josh. Okay? Ayan. Wait lang dyan ako. Naririnig? Okay, good. So, ayan. Sabihan mo ako kapag medyo hindi ganun nakalinaw yung sounds ko So, salts whose ions are aprotic. So, like what I mentioned, aprotic salts will produce solutions which are near pH 7. So, like what I mentioned, no, yung sodium chloride, pag nilagay mo yan sa tubig, ang pH niyan ay 7. Kasi, bakit? Mixture kasi siya, yung salt mixture siya ng strong base and strong acid. Like what I mentioned, sodium chloride is the product of your sodium hydroxide and HCl. Can you give me other aprotic salts, Josh? So, product siya dapat ng strong acid and strong base. Meron ka pa? Very good. KCl. Good. KCl is also an aprotic salt. Ano pa? Okay, correct. Rubidium chloride, you have a lot of aprotic salts, no? Yan. Yung mga yan, dahil strong, except francium chloride, I cannot confirm francium chloride kasi francium is radioactive, no? So, ayan. Mahirap siyang i-observe. Ano yan? For what francium is, theoretically speaking, it must produce an aprotic salt as well. Good. So,
4 million po.
how
4
about
million.
this one, Josh? Ammonium chloride. Paano kaya ito? Mamaya na. Ay, ito na pala, no? Meron pala. No? So, later. So, ang aprotic usually, ano sila, mamaya ano yan eh, mamaya ko i-example. Aprotic product sila ng strong acids and strong bases. Ang susunod ay, mga salts, when you dissolve them in water, you will produce anions that are proton acceptors. So when you say proton acceptors, they will act as acid or base anions. Proton acceptors, acid or base, Bernoulli acid or Bernoulli base. Proton acceptors. Ano tong mga to? Okay, good. So, kaya yung sinabi ko sa iyo kanina ha, wag mo rin kakalimutan to sa organic, very important to. Anions, or usually proton acceptors, will act as your base, no? Conjugate bases yan. So, conjugate bases are usually proton acceptors. If you will do this, you'll have sodium acetate. Yeah. Usually, sa ano yan, nasa organic, hindi kasi lahat ng base sa organic ay anions. Let's say ammonia, wala namang charge yun, pero base siya, di ba? So, you can also have neutral na compounds. Kunwari, water. Ang water, pwede rin naman mag-act as base, di ba? So, pero hindi naman siya charge, hindi siya anion. Kaya sabi ko lagi, usually, anions will act as conjugate bases. They're also proton acceptors. So example, sodium acetate tsaka KCN. So let's try KCN. Ang KCN saan galing, Josh? Sige, sulat. Saan galing ang KCN? So ito metal, madali naman to eh. KOH. Yan. Strong base, no? Yan. From KOH tsaka HCN. So KOH is a strong base and HCN is what? Weak acid or weak base? Weak acid or weak base? So, okay, good. So, since ito, tingnan mo ha, sino yung strong part ni KCN? Yung strong part ni KCN ay si K, no? So, therefore, KCN will act as a conjugate base, no? So, anion ito, no? So, magkaka-anion si cyanide to be specific. Cyanide ay kayang maging proton acceptor. So, anong hydrolysis reaction for KCN? What is the hydrolysis reaction for KCN? Sulat mo. Si CN na lang, nadidissolve siya sa tubig eh. Matik naman yun, Josh eh. Madidissolve siya. CN, CN hindi radical, no radical. CN minus. Yan, hydrolysis. Tapos, double-headed arrow will form, ayan, HCN plus OH minus. So, di ba, OH minus yung nabubuo mo. So, ibig sabihin, ang mga anions na proton acceptors, they are they are um, basic salts. Ito yung sinasabi ko sa'yo, no? Basic salts. So, same yan sila ni sodium acetate. Yeah. So, si Casey and Josh, ha? Basic salt siya. Tapos, poison. Technically, poison siya kasi cyanide yung binubuo mo. No? Cyanide, tapos may HCN ka pa kapag nakalagay siya sa tubig. Next. Ang susunod naman ay salts which produce cations that are proton donors. Usually, onti lang to, no? Onti lang yan. Mga ammonium lang yan, no? Kasi si ammonium lang naman ang pwedeng mag-act as acid eh, proton donor. Yan, acid yan, no? Conjugate acid. So ngayon, ang mangyayari dito, Josh, no? So let's say ammonium chloride. So ang ammonium chloride, saan galing, Josh? Ammonia at saka HCl. Correct? Sino yung strong part ni ammonium chloride? Si chlorine, no? So therefore, ano siya? Acidic or basic salt? So yung chloride mo ba kaya mag-undergo ng hydrolysis? Chloride, kaya mag-undergo ng hydrolysis? X. Very good. Hindi. However, si ammonium, kaya niya mag-undergo ng hydrolysis. Write the hydrolysis of ammonium. Hindi kaya ni chlorine ha, kasi Cl yung bubuin, HCl yung bubuin niya, magdi-dissociate lang din yun, no? So, that is the hydrolysis of ammonium ion. Very good. forming, ayun, ammonia ang nabuo. Oy, ammonia mo, may charge ba? Organison. No charge for ammonia plus H3O plus. Okay. No, not plus 3. Anyway, that is the formation of your hydronium ion out from ammonium ion. So, ammonium ion or pag yung mga cations mo ay nag-act as conjugate acids or proton donors, they are known as acidic salts. Acidic salts. So, paano kapag ganito, Josh? Parehas weak yung pinanggalingan nung salt mo, no? So, ngayon, both cation tsaka anion, no? Cation will act as an acid, anion will act as a base. Katulad nito, ammonium cyanide, no? So, paano ngayon yan? So, yung ammonium cyanide, it's a double salt, no? So, double salt ba ang term? Hindi double salt yung term dyan. Solubility product. Acidic. Walang term. Cations that are acids, hindi siya zwitter ion. Hindi siya zwitter ion. Kasi yung ano niyan ang meaning nitong nung salt na to, yung cation niya pwedeng mag-act as conjugate acid. Tapos yung anion niya naman pwedeng mag-act yung cation niya pwedeng mag-act as conjugate acid. Yung anion niya kaya mag-act as conjugate base, no? Parehas siya. Mas simple nga yung calculation nito actually. Anyway, so let's say ammonium cyanide is an example. So kita natin no, ammonium kasi kapag dinisolve mo to sa tubig, yung ammonium cyanide, it will form ammonium ion, tapos will undergo hydrolysis like this, and then cyanide ion, which will undergo hydrolysis like this, no? So therefore, both siya, no, dual yung ano niya. Nakalimutan ko yung term dito. May term dito eh. Hindi siya double salt. Yung double salt kasi, dalawa yung, kunwari, cation mo. Sodium magnesium sulfate, yon double salt yon kasi dalawang metal ions yun. Pwede rin yung double cations, let's say magnesium magnesium chloride bromide. Yeah, I think meron nun, pero bihira yun. No? So, double salt usually dalawa yung metal mo. No? Dalawa yung cation. Okay, let's study them one by one. Yeah, ano ko lang muna. Annotation. Let me clear all the drawings first. Yan. So salts which produce anions that are proton acceptors. So let's say, meron kang acetate, nag-react ka ng, or anion rather, hydrolysis with water will form the weak acid. So ito yung weak acid mo. And then, you'll now have OH minus. Pakitandaan ito, Joshua. Ito na lang yung mga ano mo dyan. Kapag ang anion ay proton acceptor, ano ang pH na ine-expect mo nung solution, nung salt solution? Dahil basic salt sila, greater than 7. Huh? Greater than 7 yung maproproduce. Next. So how do we solve for this? So madali lang no. So the dissociation or the hydrolysis equilibrium constant, KH. Yan. I introduced to you another concept, KH. The KH is equal to KW over KA, which can be rearranged into this. Ngayon, ganito yung mangyayari, Josh. Pwede mo itong i-rearrange into this, no? H3O plus is equal to square root of KW times Ka all over concentration ng HA. Mali nga ito, dapat concentration ito ni A minus. Nung salt, no? Kasi salt ang nabubuon mo eh. So this is the concentration of salt. Ayan. Sige nga, try mo to i-solve. Ayan. Para magising-gising ka ng onte. Suppose 0.2 molar sodium acetate is dissolved in sufficient water. So parang ginawa mo lang, gumawa ka lang ng 0.2 molar sodium acetate. Calculate mo daw yung pH ng solution, tsaka yung hydronium ion concentration. Also compute the degree of hydrolysis of the acetate ion in this concentration. Sige, let's try. Sige, ako muna mag-solve. So what is your KW, Josh? What is your KW again? Okay, good. So KH is equal to 1 times 10 to the negative 14. And then, what's your Ka for acetic acid? Dali lang to. Acetic acid, good. 1.75 times 10 to the negative negative 5. So 1.75 times 10 to the negative 5 is equal to square root of, ganyan din siya. Is equal to H3O plus. Let me erase this. Ganun din naman. So, ito rin siya. 1 times 10 to the negative 14 times 1.75 times 10 to the negative 5 all over 0.2, which is equal to your hydronium ion concentration. So with that, kunin ko na lang siya, no? Hindi pa na to equal. Wait, Josh. May mali ako. Sabi ko, parang may mali dito. Hindi equal yan. Ang equal ay si H3O+. Yan. KH. Ito yung KH value or the hydrolysis. Ibabox ko lang siya, ha. This is your hydrolysis value. Okay? So, which is, simplify ko lang hydrolysis value mo. 1 exponent negative 14 divide 1.75 exponent negative 5, which is 5.71, which is actually ito yung KB, no? Kung makikita mo, siya yung KB ni acetate. Naalala mo, di ba? KW, tama, di ba? KAKB, siya yung KB nung acetic acid mo. So, ngayon, H3O plus is equal to this term. So, square root, then 1 exponent negative 14, ito times mo lang sa 1.75 exponent negative 5, all over 0.2. This is your hydronium ion concentration. 9.35 times 10 to the negative 10. And what is the pH? So, just get the negative log of that. So, 9.02. 9.03. Okay. That is the pH, 9.03. So, ang pH mo, tingnan mo yung pH mo. Ano yung ina-expect mong pH? Di ba greater than 7 kasi basic salt naman siya. So, we can clearly see na 9.03 siya. Tapos, to get the degree of dissociation or degree of hydrolysis rather, no, ng acetate ion, pwede mong puntahan to. So, 5.71 times 10 to the negative 10 is equal to, you will notice, H3O plus. Yes. Hindi ba to OH minus muna yung makukuha? Ang pang OH minus ito. Or H3O plus. Yeah. Okay. Tama na yan. Kung makikita mo dito, yung 9.35 kasi times 10 to the negative 10, siya yung magiging H plus mo. So ngayon, we can easily get the OH minus, no? Kunin mo lang naman yung POH yan. 14 minus answer. So, then shift anti-log negative answer. Yan. This is your OH minus this time. 1.069 or 1.07 times 10 to the negative 5 molar. So ngayon, tignan mo dyan siya, saan manggagaling yung OH minus mo? Dito kay A minus, no? So yun yung magiging degree of dissociation mo. So OH minus, so let me erase this. Degree of hydrolysis, kumbaga. So the degree of hydrolysis is equal to, ang nabuo mo lang ay 1.069 times 10 to the negative 5, no? Out of 0.2 molar. Ita-times mo lang yan sa 100%. That is the degree of hydrolysis. Ano nga to? 1.069 exponent negative 5 divide 0.2 then times 100. So, mababa, no? 0.005. 0.005%. Ganyan lang kaliit yung nabubuo mo, no? Di ba parang imaginein mo, pag naglagay ka ng sodium acetate and the concentration is 0.2 molar, you will only produce 1.069 times 10 to the negative 5 molar OH minus out from that salt, no? So which is 0.005% degree of hydrolysis. Okay? So, yan ngayon yung degree of hydrolysis. Yan. O, dahil dyan, ikaw naman to. Salts which produce cations that are proton donors. Kahit hindi ka na ano ang tawag dyan? Mag-jamboard. Pwede mong isolve siya dyan. So, same din dito, no? This time, your cation will react with water, forming your base and then hydronium ion. So, the formula this time is H3O plus equals the square root of Kw times the concentration of your conjugate acid, the salt, no? Pag natunaw na siya, all over Kb square root, no? So, ang tanong lang dito, what is the Kb for an aqueous solution of ammonia if 0.1 formal or formal is molar lang din? No? So, the same lang din yan, Josh. 0.1 formal ammonium chloride has a pH of 5.13. Solve mo. O, dapat may tamang value dyan. Alam naman natin yung Kb ni ammonia. So, dapat yan yung masasagot natin. Let's confirm, no? Kung tama yung mangyayari. Sige, solve mo. What is the Kb of your ammonia?
Bakit po formal yung ginamit niyo po sa doktora?
Same lang din yan. Ang formality is, actually, ang term na formality, old form siya ni molarity. Okay? Na-meet mo na ba ito si
Why
formal?
don't we just call it why don't we still call it formality po?
Para lang ma-familiarize ka na ano, ganun din siya. Formality is just molarity. Ano na nga siya, medyo obsolete na siya eh. Onti na lang yung gumagamit ng formality. Onting books na lang yan. Ngayon, to make it easy, formality is equal to molarity. That's also molarity. Ini-introduce ko lang sa iyo ha para hindi mo siya makakalimutan. Formality is just molarity. Formality refers to the moles lang din. Sulat nung solution. Good. Times yung concentration ng salt, which is 0.1 lang din. Solve mo. Ship solve. Pwede naman yan ship solve. Negative 6. Okay, correct. 1.82 times 10 to the negative 5. Is this close dun sa declared Kb ni ammonia? Ano yung declared Kb ni ammonia? Yes. The declared Kb is 1.75 times 10 to the negative 5. Okay na yan. Ano naman kasi ito no? Syempre, hindi natin, kung kumbaga sa analytical chemistry to, hindi natin chinek kung tama ba yung formation or yung pagkaka-prepare, no? Preparation ng 0.1 molar ammonium chloride. So for sure, nag-calculate lang yung nag-prepare niya ng 0.1 molar ammonium chloride. So meron kang mga error sa weighing, may error ka sa mismong dissociation, etc. Tapos yung pH meter mo, pwede ring may error siya, no? Hindi talaga siya 5.13. So let's say 5.135, 134. So it will make your calculated Kb for ammonia, quite ano no, quite near naman siya pero not exactly dun sa declared value ng Kb ni ammonia based sa books, no? Or in reality na nakikita natin. Okay na yan, 1.82 times 10 negative 5. Calculate mo nga error dito. Relative error. What is the percent relative error there, Josh? Sige, anong percent relative error mo? So, percent relative error is EV minus TV all over TV, or experimental value minus your true value all over true value times 100%. Uy, 25% yung error mo. Ang laki niyan. Eh, magkalapit naman sila ng value. Dapat magtataka ka pag mga ganyan. 1.82 times 10 to the negative 5, tapos 1.75 times 10 to the negative 5, di ba? Ano, 1.82. So, experimental value mo si 1.82. Kasi siya yung nakuha natin sa calculation. Eh. Tapos yung true value, yung mga nasa books, no? Si 1.75 times 10 to the negative 5.
Tama po.
Anong sagot? Times 100. Oh, 4% lang, hindi ano, hindi hindi yung 25% kanina. Sabi magtaka ka doon, ang laki ng error mo, no? So, 4% error, no? Kung ibig sabihin yung experiment na yan, may 4% error siya. Relative error na nagawa. Next. So, ako ulit to. Okay. So, salts which produce cations that are acids and anions that are bases. So, if you will notice here, dalawa sila no sabay. May A plus ka na. Balik ako dito. Yan. May A plus ka na mag-a-act, na mag-perform no, ng base. Tapos, may A minus ka na mag-perform ng weak acid niya. So, paano ngayon yun? So, if you will notice the hydrolysis expression constant, you now combine everything. Yung Kw ni water, tapos yung Ka nung acid mo, no? Yung may, eto, yan. Yung Kb ni A+, then combine everything here, no? So the species na A, then Ha all over A+, then A minus. So, ngayon, if you will notice, we can actually cancel out some species there once you manipulate or substitute everything. So, magiging H3O+, mas madali ito, no, Josh? Si H3O+, if you will notice, nagde-depend lang pala sa Kw, sa Ka, at sa Kb ng mga salts mo. No? So, ngayon, example. What is the pH of a solution which is 0.1 formal in respect to ammonium cyanide? Calculate the percent hydrolysis of the salt. So, regardless of the concentration, Josh, you don't need the concentration this time, no? Because it will end up having the same hydronium ion concentration. No? So, kasi nga, mag-a-adjust yung mismong system mo because of its Ka and Kb nung magkaibang ions mo, yung cation and anion, so that you will gain that H3O+. So, calculate the percent hydrolysis of the salt, which is Kb. Kb for ammonia is 1.8 times 10 to the negative 5, while for cyanide, it's 7.2 times 10 to the negative 10. So, direct substitution na lang siya. The square root of 1 times 10 to the negative 14 times your Ka, which is 7.2. This is wrong. 7.2. 7.2 times 10 to the negative 10 all over your Kb is 1.8 times 10 to the negative 5. So, if you will notice, the answer for that is 1 exponent negative 14 times 7.2 exponent to the negative 10 all over 1.8 exponent to the negative 5. So the answer is 6.32 times 10 to the negative 10. So the pH for this is, just take the negative logarithm of that, 9.19 or 9.20. So this is still basic. So basic yung nabuo kasi si cyanide, no, ang mas naging stronger na species kumpara kay ammonium ion. Tama ba? Yes, ammonium dapat kasi ay ammonium plus OH, okay, H3O plus. Si cyanide, okay, kuha OH minus. So si cyanide yung mas parang nangibabaw dyan. No? So yung pH mo ngayon ay 9.20. Okay, so just remember this equation. Pag mga salts na both yung cation niya ay magiging acid at ang anion niya ay magiging base. Okay? So, this one, siguro dito tayo magtatap. I mean, di ito yung end topic natin ha, pero tapusin natin tong KSP. So, we ended up now with the salts, no? So, mga hydrolysis reaction. Ngayon, Josh, kung mapapansin mo, yung salts natin dito ay completely dissociated in water. No? Ay, itong mga hydrolysis, Josh, ito. Itong mga hydrolysis mo na reactions, applicable yan sa mga completely dissociated in water. Ako, babalik ako dito ha. They are completely dissociated in water. Kaya kung mapapansin mo, or completely dissolved in water. Kung mapapansin mo, Josh, dissociated mali yung term ko, completely dissolved in water. Kung mapapansin mo, yung mga binibigay ko ay mga nadidissolve sa water fully. No? Or virtually speaking, they can be dissolved in water. Okay? So, kasi kapag partly soluble ang magiging salt mo, iba ngayon yung associated equilibrium constant. The equilibrium constant must be KSP. Okay? So KSP is your solubility product constant. So we'll now be talking about solubility product principle. So actually this is a review to you, no? Kasi yung unahang part natin, yung the way we discuss the ice table, etc. This is the example. So, and we're always talking about solubility for the longest time, no? For the longest time, we're talking about solubility, solubility product, etc. Na mention din natin siya sa ibang topics natin. So, we'll have a run-through for this, no? So, we'll have a partly soluble metal, MX, no? Or salt. So, this MX can be dissolved in water partially to form M plus tsaka X minus. So, if you will notice here, dahil insoluble ba, insoluble tuloy, partly soluble, or pwede rin nating i-term, no, virtually siya insoluble, pero theoretically, may nadidissolve talaga. No? Pakitandaan nyo siya, yung term na insolubility, hindi siya ganun ka-correct para sa akin ha. Kasi kung iintindihin mo, based sa solubility product principle, meron at merong nadidissolve na ions coming from your salt, no? Pero minsan, sobrang onti lang. Kaya hindi siya natin nakikita, no? Visually, or in reality, we cannot appreciate it because we cannot see that the solid we're mixing with the liquid, it's not getting dissolved, no? But as much as possible, or in theoretically speaking, you will still have some ions formed from your salt, no? So with that, you'll have KSP. So KSP is equal to, of course, dahil ito ay solid, Josh, tatanggalin mo to sa equilibrium constant expression. So you'll only have M plus and X minus, no? So then raise to there, coefficient. So minsan kasi nagkaka-coefficient yan, no? So dito 1:1 lang naman. So 1 and 1 lang to. Pero wag mong kakalimutan ha, meron yang mga nag-i-square, minsan may nagkukube dyan. So a very small solubility product value indicates a very insoluble compound, which is correct, no? So pag mas maliit yung value, ibig sabihin nun, physically speaking, reality or in visually, pag pinerform natin siya sa lab, makikita natin yung salt ay hindi talaga nadidissolve sa tubig. Pero, meron at merong nadidissolve dyan. Kasi maliit nga lang yung KSP niya. Very small KSP. Solubilities of most substances increases with rising temperature. So therefore, the values for KSP also increases with rises in T. So, if you will notice, Joshua, kunwari, ito yung KSP, 10 to the negative 35, kunwari, at 25 degrees Celsius. Ngayon, kapag tinaas mo yung temperature into 50 degrees Celsius, let's say naging 10 to the negative 15 na lang to. So, ano nangyari dito, Josh? Sino yung mas mataas yung value ng KSP? 50 degrees Celsius or 25 degrees Celsius?
50 siguro po.
Which one will have a higher KSP value? 25 or 50 degrees
Wait.
Celsius?
Negative 35 to.
Yung isa negative 15.
So, higher yung 50.
Higher yung?
Higher yung... Yes, 50 po.
Okay, correct. 50 degrees Celsius. So what do you expect? More ions or less ions? Or more solid ito? Ayan yung equation mo. Mx going to m plus x minus. So dissolution, no? Dissolution lang naman yun.
More ions po.
At 50 degrees Celsius. So anong ibig sabihin nun? How can you interpret that? Pag more ions.
More ions. Mas dissolving po.
Very good. So at 50 degrees Celsius, mas nadidissolve siya. Pakitandaan Diyos siya, ang KSP ay nag-i-increase together with temperature. So temperature is directly proportional with KSP. Okay ha? Tandaan mo yan, Josh. Kasi meron yan dyan yung mga simpleng tanong lang na, kunwari, among the following, blah, 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 at 50 degrees Celsius, which one will be soluble in water? Or ano nangyayari sa KSP with increasing temperature? Huwag ka naman dito dyan. The higher the temperature, the higher the KSP. Yun lang. Okay? The solubility of very small crystals of a sparingly soluble salt is greater than that of a larger crystals of the same salt. That's the reason why it's very important for us na finely grind or finely ground yung mismong um, mismong salt mo. So that you'll have yung third statement mo, Josh, anong factor affecting solubility yan? Regardless naman kasi kung insoluble or soluble or insoluble siya, Josh. True yan. It holds true. The third statement holds true regardless if it's soluble or insoluble in water. What is the reason for that? Very good. Surface area lang. Larger surface area, higher solubility. No, so, kaya regardless kung insoluble siya, kung sobrang fine nung mismong salt mo, no, it will still produce more ions, no? Because water can easily interact with your finely ground na particles. So, examples of your solubility of slightly soluble salt, let's say silver chloride. So, silver chloride, Ag plus Cl minus. So, the KSP is this one. Can you give me the value for this? Anong value nito? KSP ni AgCl. Ito may usual to Josh eh. 10 to the negative 10 yata to eh. Or 10 to the negative 11. Hanapin mo, KSP, AgCl. Kasi usual yan. Kaya gusto ko maging familiar ka kay AgCl.
1.6 times 10 to the negative 10.
1.6 times 10 to the negative 10. Tama ba? Yeah. Dito nga 1 times 10 to the negative 6 lang. Ay, AgCl to?
Opo.
Anong KSP mo ulit sa AgCl?
1.6 times 10 to the negative 10.
Negative?
10.
KSP, AgCl. Hanapin natin. Yun, AgCl. 1.8 times 10 to the negative 10. O tama nga. Tignan mo tong ano natin, preference. O ayan o. Feeling ko ano to, typo to. 1.0 times 10 to the negative 6. Ang KSP niyan 10 to the negative 10, natatandaan ko pa nga eh. Dito sa na-search ko, 1.8 times 10 to the negative 10. Okay? So, Ag2C or CrO4, silver chromate. Can you search chromate?
1.2 times 10 to the negative 12.
1 point
1.2 times 10 to the negative 12.
negative 12. So, ang na-search ko, Joshua, pakitandaan, ang mga KSP, medyo malaki yung variation nito from reference to reference. Pero dapat, yung mga 10 to the negative nila, same yon. Tignan mo itong na-search ko Ang na-search ko, 9 times 10 to the negative 12. Maisipin mo, no? Ang layo naman nung 1.2 sa tsaka sa 9, no? Pero ang mahalaga dito, 10 to the negative 12. Maliit na kasi masyado yung value nitong mga to. So ngayon, pag ginagawa sila sa experiment, minsan range yung nakukuha mo, no? So, malaki yung range na nakukuha. Ngayon, I have a question, Josh. Which one is more soluble? In water, AgCl or Ag2CrO4 with respect to their KSP? Sinong mas soluble sa tubig?
Yan
Technically,
ako.
insoluble sila. Ha?
AGCL. AGCL.
Again? Which
AGCL.
one is more soluble in water?
AGCL.
Very good. So, kumpara, based lang sa KSP, no? So, this is more soluble. However, virtually speaking or physically speaking, AgCl is still insoluble in water. Okay? Pakitandaan yan dyan siya, insoluble pa rin naman siya sa tubig. However, ganyan nga yung comparison, no? Comparison-wise, mas soluble sa AgCl kumpara kay Ag2CrO4. Next. So, with this given, no, with this given table, sino yung pinaka-insoluble? Grabe, no? Sulfides. Josh?
So,
Sulfides. Napaka-insoluble ng mga
bakit po yung
sulfides.
HGS extremely insoluble?
Hmm?
Bakit po yung HGS extremely
AG,
insoluble?
again?
So,
AGS?
in HGS po.
Mercury sulfide?
Ako.
Extremely insoluble siya, no? Tingin mo, bakit?
HG po, double whammy.
Hindi. This one lies on their bonds. So, kahit ionic sila, yung ionic bond nila ay really strong na even water cannot break them. Yun ang lagi mong tatandaan na, Joshua, para kasi pag naiisip natin in chemistry, in a general sense, salts are ionic compounds. That's true. Ionic compounds yung mga yan dati. They're made up of electrostatic attraction, cation and anion. So therefore, parang dapat madidissolve sila ni water.
So,
Not
safe po,
true.
technically po safe kainin kasi hindi naman siya mag-dissociate into mercury.
No. In ano, no? In essence, theoretically, yes. Tama ka doon, no?
Why
Napaisip ko
wouldn't
doon.
you want to try it?
No, I don't want hypothetical. Even hypothetically speaking, I don't want to try that. That's true, no? Pero tignan mo,
Pero yun
KSP,
po yung practical science. If
may
it's really that
KSP pa rin
insoluble,
siya.
if it's really that insoluble, then would you eat it?
I think at some point in our lives, we've eaten already these things, pero very, 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 very small concentration. HGS, AG2S, tapos dahil sobrang
Pero
liit ang concentration,
may mercury po in our, in our drinking water. Very little
yeah.
though.
So, sobrang liit nga lang, no? So, sabi ko nga, ang ano naman natin sa Anakem, concentration ng labanan dyan. So, toxicity will have its own limit based on the concentration of your toxic material or toxic substance, no? So, pero that's true, no? Theoretically speaking, tama ka naman. We can eat, no? HGS. Kasi in our body, it will not be dissociated into mercury tsaka sulfide ion, no? Due to its very low solubility, very watery yung ano natin yung katawan. However, Josh, meron akong isang panabla dyan. Dadaan kasi siya sa acid mo, stomach acid. Mm. Will you want to eat pa rin HGS? So no, it's still a no. So HGS will be soluble in acid already. So medyo magiging soluble na siya sa ano mo, stomach acid. So therefore, wala, mafi-free up nyo, yung mercury ion dyan. So ang answer, no, hindi pa rin siya pwedeng kainin. So,
No.
we can clearly see here, no, yung rule na SCOPO, sulfides, carbonates, phosphates, and hydroxides, sila yung mga insoluble talaga in water, no? Sulfides, hydroxides, carbonates, phosphates. Yan ang mga insoluble in water. Okay? So, we still have some ano no, some notes na binabalikan lang. The molar solubility depends on the stoichiometry of the salt. So, a 1:1 salt, tingnan mo to, is less soluble than a non-symmetrical salt with same KSP. May reason for this, no? Kasi pag 1:1 yung salt mo, Josh, mas stronger yung binding nila. Kumbaga, kasi 1:1 lang naman sila, no? So, the ionic bond will be stronger between these two salt. Actually, may iba pang curie for solubility product, Josh. Pero sa advanced inorg natin siya iti-take, no? So, yung mga ilang inorganic sa chapters natin na hindi mo pa natitake, like yung mga symmetry, point groups, etc. Tsaka yung acids and bases, doon natin yan iti-take, no? So, hard soft acids and bases dun yan. So basta tandaan mo lang yung pattern for Anachem, no? Kasi si analytical chemistry ang concern niya ay ito yung value, no? Yung KSP. If you will notice, try natin mag-iset, no? Or try natin i-check. Tingnan mo to, Josh. Yung mercury sulfide na 1:1, mas insoluble siya kumpara kay silver sulfide, no? Na dalawahan. Tatlo kasing atoms ito no? So, pwede ring ito. Ah, wala kasi tayong aluminum sulfide, no? So, let's try to look for aluminum sulfide. Walang aluminum sulfide. Calcium hydroxide. Calcium hydroxide. Ayun. Yung calcium hydroxide ko, Josh, ay 7.9 times 10 to the negative 6. Ilang atoms or ilang groups ang meron sa calcium hydroxide, Josh? Hydroxide? Calcium hydroxide, ilang groups yon, Josh?
1, 2, 3.
3, correct, no? So, 2 hydroxides, then 1 calcium. Calcium sulfide, on the other hand, that's 1:1. 1 calcium and 1 sulfur atom. 8 times 10 to the negative 6. Slightly higher, no? So, yun yung sinasabi ng rule na to. No? Ito yung sinasabi ng rule na yan. A 1:1 salt is less soluble kumpara dun sa non-symmetric salt. So, calcium hydroxide, ibigay natin yung example. Ang KSP nito ay, based sa nakita ko, 7.9 times 10 to the negative 6. Less lang naman However, ang calcium sulfide, ang KSP niya, very near, no? 8 times 10 to the negative 6. So, yan. Mas soluble lang tong si calcium hydroxide. Tama ba? Higher value. Yes, higher value. Ito. So, this one is less soluble. Okay? Less soluble. So, pag may common ion effect, nakita na natin to yung sinolve natin, yung lead iodate. Kung naalala mo, no? This will decrease the solubility of a slightly soluble salt. Insoluble na nga siya, mas lalo pa natin siyang magiging insoluble pag may common ion effect. Pakitandaan to ha. Ulit Josh ha. Common ion effect in a solubility, in a partially soluble solid will decrease the solubility of that slightly soluble salt. Okay? So, na-prove naman natin siya last time. So, this is the graph nung common ion effect. So, tignan mo to ha. The common ion effect is used to decrease the solubility. So, tingnan mo. Anong nangyayari kapag ini-increase natin yung barium concentration. So let's say may barium sulfate ka, Josh. Ito yung solution mo, tapos ayan, may soluble ka dito, no? Insoluble na barium sulfate. So, ngayon Josh, tingnan mo. Kapag ini-increase mo yung concentration ni barium 2+, kunwari, nag-a-add ka ng barium chloride, anong nangyayari sa sulfate ion mo? Josh, barium 2+. Kunwari, ini-increase mo yung barium 2+.
When in-increase po, bumababa yung solubility at bumababa yung SO4.
Kung bumababa yung sulfate, anong nangyayari sa sulfate? Nako-convert siya into?
Nako-convert into barium sulfate.
Correct. So, ano nangyayari sa solubility?
Bumababa po.
So, kasi you are forming more barium sulfate. So, bababa talaga. Yan ngayon yung graph. Ganito ang graph ha. Minsan kasi, may mga questions lang na paano ang graph ng common ion effect in slightly soluble salts. Ganyan siya. Okay? So, ayun, may meeting din kasi ako, Josh, ng 7:30 siya. So, nag-start na daw sila. Pero dahil nag-start tayo ng mga 7:45, we'll solve lang number 13. So, next meeting ha, we'll have the rest ng, ayan, may salt effect ka pa, diverse ion effect, tapos activity. Ayun, malapit na tayo matapos. So, anyway, solve natin tong si 13. Ako muna magsasolve nito para ikaw si 14 and 15. So, if the solubility product constant of lead phosphate is 3 times 10 to the negative 44, what is the molar solubility of this compound? So, let's write first the solubility reaction of lead phosphate. Kung anong formula ni lead phosphate, Josh? Pb, lead phosphate. Ay, Josh, anong formula ni lead phosphate?
Yung PbSO4 lang? Or Pb2SO4?
Hindi, phosphate. Phosphate, hindi sulfate.
PbPO, ha? Na-rare po to ha.
PO?
Hindi ko po na-encounter.
Oh, pero
PbPO2,
ayan, may encounter mo na siya
PO4,
ngayon.
PO4,
PO4?
for PB2, PO43, or PB3,
Baliktad.
PO42,
PB?
3, PO42.
Very good. 3, then 2. So, this is slightly soluble, no? So, ilang lead ang mabubuo, Josh? Ilang lead? How
Ilang
many lead
LED?
ions?
3.
Okay. Kasi, problema mo yan mamaya sa aqueous ito. Problema natin siya mamaya, no? Then, 2 phosphate ions. Aqueous. So, therefore, anong KSP expression natin? So, KSP is equal to PB 2 plus raised to what? PB2 plus raised to,
PB2 plus raised to yung 3. 3. Cube.
okay, and then phosphate raised to
Okay.
2. So, di ba lahat naman sila manggagaling, tingnan mo Josh ha, lahat sila ay manggagaling lahat kay phosphate, no? Lead phosphate. So, X to, so 3X and then 2X to. So, this is equal to, the KSP is 3 times 10 to the negative 44. So, therefore, ilang PB2 plus ang maano mo sa ice, Josh? Kunwari nag-ice table ka at equilibrium. So, X naman to eh. Ilang PB? So, 3X at equilibrium, then 2X. So, this is 3X cubed times 2X squared. So, this is equal to, 3X cubed is equal to what, Josh? 3 times 3 times 3. 3X cubed, Josh. Simplify mo to, Josh.
3X. So, wait. 27, 4, 4, 8, 108, 108x to the 5th.
Okay, very good. So, ngayon, 3 times 10 to the negative 44 is equal to 108 x raised to 5th. So, para makuha mo yung x, this is equal to the 5th root, no? Ng 3 times 10 to the negative 44 all over 108. Very small, no? So, kaya ba ng calcul natin yan? Oy, solve mo, Josh. Yes, kaya ng calcul natin. 5th root, that is 3 exponent to the negative 44 over 108. Josh, anong sagot mo?
7 4 times 10 to the negative 10.
Very good. 7.7 times 10, 7.74 times 10 to the negative 10. This is your solubility. So, sino yung x mo? That is your value, no? So, actually, x pa lang yan. Yung PB2 plus at equilibrium is ita times 3 mo yan. Times 3, that will be, syempre, ito yung nadidissolve na PB3PO4, no? Ayan yung nadidissolve na PB3O4. Ito na yon yung solubility. Pero if you want to get the concentration of lead-2 plus and phosphate ion in your, at equilibrium, you multiply it with 3 para dun sa lead, which is 2.32 times 10 to the negative 9 molar. And then sa phosphate mo, Josh, ita times 2 mo lang siya. So, 7.74 exponent negative 10 times 2, 1.55 times 10 to the negative 9 molar. So, yan ngayon yung concentrations at equilibrium. Okay, so I think we're good with this one. Next meeting, Joshua, will continue yung KSP. Tapos, we'll now have the salt effect and the diverse ion effect. These are new to you kasi alam ko hindi to tinuro ni Sir James. Kasi nga, sa ano to lalabas? Sa,
Hindi
naturo na rin siya?
po. Hindi po.
Hindi pa. So, kasi sa Anakim niya talaga, sa Anakim namin yun iiwan eh. Yung salt effect at diverse ion effect. I'm pretty sure ito rin, hindi ito tinuro. Kasi itong activity ay sa Anakim lang din yan. So, this is a new to you, no? Parang ganito kasi yan. Pag may concentration ka, Josh, are you really sure na ang 0.1 molar sodium hydroxide mo ay 0.1 molar talaga? No? Kasi nagkakaroon ng effects yung mga charges. No? So, ayan, may mga table dyan, tapos may formulang ganito. The Debye-Yukel equation, no? So si Debye tsaka si Yukel, mamimit mo na sila. So, sa ano yan, di ba? Sa physics natin sila namimit, pero may application sila sa mga size ng atoms kasi. Yan, mga crystallography and all, makikita mo ulit sila. Okay? So, ayan. With that, Josh, sa Thursday, we'll have the continuation of this. Okay? So, we're good for tonight and I hope to see you on Thursday. Okay na tayo, Josh?
No po.
Okay, sige, sige. Good night and regards to your mom and dad.
Bye-bye po.
Sige. I'll just end the meeting.